All right, so we have Lorenzo Leandro from Quantum Machines, please.
Hello, everyone. I hope you are all alive after a night of hacking. I will attempt to keep you awake for 20 more minutes, discussing a little bit about quantum machines and a little bit about the integration of quantum and classical computing. So, at Quantum Machines, our mission is to accelerate the realization of useful quantum computers, and we're not there yet, obviously, and I'm very happy that this hackathon was made very clear that the word useful is kind of the tricky part here, since we haven't realized an application that is useful to society yet. Quantum Machines, at Quantum Machines we are a bunch of quantum passionate and experts. We are about 140 people now, vast majority of which with PhDs in quantum related fields. And we try to accelerate the realization of useful quantum computers by bringing real-time control into the picture. And we do this by integrating quantum and classical resources. And I'm going to attempt to discuss this a little bit and make it a bit more clear. So if we open a quantum computer and we start discussing what quantum computers are and so on and so forth, we usually talk about qubits. So we talk about quantum processors. In reality, if we want to do something useful with a bunch of qubits, we have to apply the gates, and these gates are usually applied with classical systems. So we have some control system, some orchestration going on that is fully classical, and that helps to send and receive pulses from the qubit, but there is also going on a quite big part of classical computation behind the circuits that you run. So let's have a little bit of a look at this integration between quantum and classical resources. So there is two big use cases, let's say, for this integration. One is squeezing performance out of the QPU. So you have your qubits, but you want higher and higher fidelities. You want to throw more gates into your coherence time and so on and so forth. And there is also the case for executing hybrid application workflows. So in the end, we're going to have, hopefully, application workflows that solve real-world problems. Those are going to be very complex, and it's very likely that they will use a combination of resources that are both quantum and classical. So the managing of this application workflow, it's going to be classical. So it's a classical problem. We have to be able to integrate classical resources with quantum resources. So if we take a few examples, so squeezing performance out of the QPU, one clear, obvious example is state preparation. If you want to reset your qubits before you do your next circuit, you're going to need to actively reset the qubit. Obviously, you can wait your 10 times T1 and have them reset on their own, but if you have 20 qubits, that starts to become to lower your fidelities. So you want to squeeze performance, you actively reset your qubits. So the easiest way to do it is you measure the qubit, then you do a classical computation checking if the qubit is 0 or 1, and then you decide how to branch your logic in the program to decide whether you want to send a pi pulse or not. All of this, it's purely classical. You need a classical system to do it, and the integration is really bringing this classical capability within the quantum time frame, let's say, within your quantum sequence. Qubits don't last very long generally, or if they do, you still want to put many, many gates together, so the faster you can do this classical computation, the better. There is also many other examples, obviously quantum error correction, dynamical circuits, all of the calibrations that you need to do to keep a QPU alive. They all use classical computation. They all use classical resources. The faster they are, the better. For application workflows, one clear example is variational quantum algorithms. So these algorithms are usually a loop between classical resources, classical computation, and quantum resources. So you run a parameterized quantum circuit, and then you use a classical computation or classical computer to process and optimize those parameters that you then feed back in the quantum computer, and you run this in a loop hoping that it will converge. This is obviously relying heavily on on classical resources. So this is a clear example of how classical resources are basically as important as the quantum resources in a quantum computer. So at Quantum Machines, we have built the quantum orchestration platform, which is a platform that allows to talk to qubits through an analog front end, radio frequency and microwave. And within, attached to this front end, we have a pulse processor. This is a quantum machine designed processor that is specifically made for quantum control. So it does four things mostly. It has a waveform generation in a fully parametric way. So this is an FPGA-based controller that is able to generate the waveforms live. So you don't need to load them in memory. They get generated during the sequence. And they also are generated with parameters that live on the FPGA as variables. So these variables can be computed upon, and they can inform the waveform generation and the logic behind. It also does waveform acquisition. Obviously, you want to read out from qubits and manipulate whatever you read out. And then also real-time processing. As we said, even the most basic active reset is an act of classical computation to do state discrimination, but you can imagine all sorts of very different computation that you want to perform for different circuits. And on top of that, you can do control flow. Control flow as in conditional statements, loops, for loops, while loops, deterministic or non-deterministic, it doesn't matter. It all runs on an FPGA, so at the shortest latencies. One example is the active reset. It's done in 200 nanoseconds. So if you imagine your sequences and whatever experiment you want to run, they usually live within a space that is spanned through these four capabilities. But this is only half of the medal. Now you have a very fancy FPGA-based controller. You need to be able to program FPGA to run it. That's not very useful. So what we did is also to introduce iQuHACK, which is the first pulse-level programming language. With iQuHACK, you can very simply, very intuitively write sequences. We're going to see an example in a few slides, so I won't say any more. But basically, whatever you type in iQuHACK on your laptop gets compiled directly into FPGA code that runs on the pulse processor. So even though you run it, you type it in Python, it gets compiled and run on an FPGA. So when we talk about quantum computers, usually we talk imagining a quantum computer as like a black box. So we have a quantum node on one side. It has its qubits, it has the quantum control hardware, and it has some software to run all these pulses. But usually when we write codes for quantum computers, we write them at the gate level on some other laptop somewhere else in the world, probably. And this usually adds some limitation in terms of how much you can optimize. So when you are here at the hackathon typing some gates to do your sequence, there is an engineer or an experimentalist from the other side of the world that has to optimize the pulses that come out, the hardware to control the qubits, in order for these gates to work and to work with high fidelities. At Quantum Machines, we are offering a different view to this problem. We take the hardware-aware software, which is the pulse-level software, and we move it onto the classical computer that you type onto. So this allows, for example, to work on the optimization that is specific to the setup. This is, again, hardware-aware, so the software knows what qubits are attached to it. And you can build calibration routines, and you can automate your sequences in a way that you optimize fidelities and operations. So this is, of course, done through iQuHACK. So you write iQuHACK in your Python environment on your laptop, then it gets compiled into a quantum orchestration system with code that runs on the pulse processor that is sitting next to your qubits. This allows for low latency and a lot of capabilities in terms of optimization of the specific system you're used to. But also, it allows easily for this hardware-aware software to connect both with classical resources that happen to be on the server or computer we are working on, and with software libraries that we are all used to, Qiskit or OpenCASM3 and whatever other standard out there. So this specific model allows to optimize for two different time frames. One is what we call the real time, which is deterministic, and it's basically comprised of all the things that you want to do with ultra low latencies. Active reset is one of the examples. There is many others, but there is things that you want to run in hundreds of nanoseconds at most. And here we're talking about classical computation and pulses, both the manipulation, readout, and the driving of pulses. But also there is another time frame, which we call near real time, which it's less strict in terms of how fast it needs to be. It doesn't need to be lower than the coherence time of your qubits. For example, all the procedures that are of calibration, tracking of the qubit frequencies, and all of these stuff, they can be done outside of the coherence time, but still need to be run fast in order to not clog the QPU utilization. You don't want to waste time calibrating. You want to run programs. So let's go back to our quantum computers. We have our quantum processor, and we also have an orchestration system. This orchestration system allows, through a pulse processor, to do real-time sequencing and real-time classical processing to help the quantum processor achieve its goals. We have iQuHACK, which is an intuitive software to help you write in a very, very simple and intuitive way the quantum sequences, and this also integrates with higher-level softwares. Let's have a look at iQuHACK just to give you a feeling of what I mean when I say it's intuitive. Let's say I want to play a pi pulse to qubit 1. That's about it, play pi to qubit 1. If I want to measure and measure the readout channel and save the raw data, that's about it, measure, readout, raw data. But I also have general variables that live on the FPGA, so I can do mathematical computation, I can do logic on these variables, and these variables, they can be used in the play commands and in all the other commands that the FPGA has to generate live. Here I'm playing a pi pulse times an amplitude, so I'm going to stretch the amplitude of this pi pulse depending on the variable A that is living on the FPGA. When you type this code, you don't necessarily know what the value of A is, but the FPGA will know once the time comes to play this pulse. So classical variables can also come from measurement. The example we had before is measure a qubit, and then depending on the measurement, apply a conditional pi pulse. Obviously, you cannot do this in Python because it's going to take you milliseconds just to communicate with the laptop. So you impose conditions into iQuHACK that gets run onto the FPGA. And of course, this is a full control flow system, so you can do an if statements, but you can also do loops. You can run 2D, 3D loops directly on the FPGA. Of course, this being run on an FPGA controller means that you have absolute time control for both phase and timing or timestamps of whatever it's happening from the FPGA. This is, of course, extremely important when you have to deal with real-time deterministic sequences. So let's take a very brief example to showcase iQuHACK. Let's say I have a qubit. I want to know what is the amplitude of a pulse to send this qubit from 0 to 1 and vice versa. This is what we call a power Rabi sequence, and that's how we can write it in iQuHACK. It's a for loop that spans through an array of amplitudes, and then I play a Gaussian that is multiplied by an amplitude to my qubit, and then I align the qubit and the resonator and measure the resonator. And this is the output of our controller, and we see the same Gaussian repeated but stretched in amplitude. So the controller only has maybe 60 points in memory defining a Gaussian, and it doesn't necessarily need to know what the amplitudes are before it needs to use them to generate the play command. And this loop runs on the FPGA. So once I run this, I can, for example, take one period, and then I can calculate what is the amplitude that I need to do a pi pulse or a pi half pulse. This is a sort of a calibration of a qubit operation. So the real power of this is not only performance, is not only the fact that I can reset a qubit in 200 nanoseconds, but it's also the fact that you can write your sequences in a very, very intuitive way. It's basically as simple as writing pseudocode. And that means that from the moment you open the box of the controller, it really takes very, very short time to implement the sequences that you have to run. This is just an example from a recent installation where the customer only took 48 hours to write all the sequences that it required to get to randomized benchmarking. So we are talking about not only the calibration and the configuration of the system, the calibration of the mixers, the stability diagrams, 1 and 2, the Rabi, Ramsey, echo experiments, IQ blobs, and so on and so forth, until readout optimization and randomized benchmarking and even more complicated sequences. It's really simple to write, and it gives you the full power of the FPGA without being able to write FPGA. So that's how, by integrating classical capabilities into quantum systems or quantum sequences, we try to bring usefulness into the world of quantum computing, and also by supporting events like this. So I wanted to thank the organizers to making this possible, to you guys to come here today, and I'm here if you want to ask questions. Thanks a lot.
Thank you so much, Lorenzo.